What is up, you guys? So in this one, we're going to be talking about a new topic called Eigenvalues and Eigenvectors. So this lecture and the next 2 or 3 are going to be around this topic, so just an overview of those lectures. Say I've got a square matrix, and eigenvalues are only defined for square matrices. Now for a large number of problems in engineering and science, it is necessary to find a vector v such that if I multiply a by v, we get a scalar multiple of v. That said, we get lambda v, where v is a scalar and not a matrix. Okay? V is a vector and a is the matrix. So if you can find me a couple scalar lambda and a vector v, so lambda is a scalar and v is a vector, then guess what? You found one eigenvalue and its corresponding eigenvector. Eigenvalues and eigenvectors are always paired up. That is, for each eigenvalue, there's a corresponding eigenvector, right? So in many problems in engineering and science, we care about those quantities that characterize the matrix A. Now, graphically, what that means is that the vector AV, don't forget that AV is also a vector, AV, so if this is V, and if we were to plot AV, in that case, we say that AV and V are parallel, and lambda V only stretches and compresses V. So lambda V, if lambda is greater than 1, it stretches V. Let's say it's positive, so lambda V is going to be on this line as well. Let's say it's somewhere here. And compresses. If it's less than 1, greater than 0, it lies here, somewhere here. So lambda V is compressing V, and AV is still parallel to V. Actually, in this particular example, it coincides with V. So graphically, this is what it means. V is a vector that, first of all, preserves the direction of V, and second of all, it either compresses or elongates the vector V. In other words, it doesn't rotate V. So the value lambda here is an eigenvalue of the eigenvector V. It is worth keeping in mind that computing eigenvalues and eigenvectors is one of the most important problems in numerical linear algebra. Eigenvalues are critical in such fields as structural mechanics, nuclear physics, biology, the solution of differential equations, computer science, signal processing, electrical engineering, to name a few. Eigenvalues also play a crucial role in the study of vibrations, where they represent the natural modes or frequency of a system. When vibrating structures begin to have larger and larger amplitudes of vibration, they can have colossal consequences. Some examples include the wobbling of the Millennium Bridge over the River Thames in London, and the collapse of the Tacoma Narrows Bridge in the state of Washington. These are examples of a well-known phenomenon known as resonance. Now, a mathematical analysis of a general model for vibrating structures shows that when the system is excited by a harmonic force that depends on time, the system, approaches a resonance state when the forces approach a particular eigenvalue. Now, later on in the course, we'll be giving applications as we did previously with different concepts such as encryption when talking about determinants or inverses, electrical circuits when talking about linear systems, and trusses as well when talking about the same topic. In a similar manner, we're going to give applications to eigenvalues and eigenvectors to have a better intuitive feeling of what those quantities really reflect. Now, do not forget that we're still talking about linear transformations. That is, we're going from one space to another via a linear transformation. So let's say we're in a 2x2 space and we're going from the traditional xy space to another space via this transformation matrix. So in this case, it's identity. That is, any point is brought back onto itself. Now, given the red shape over here, we'd like to see how it's affected by different transformation matrices. So let's say we're given this transformation matrix. Now, the blue shape that looks like a horse is elongated along the x-axis, whereas it's preserved along the y-axis. Now, this is where eigenvalues and eigenvectors come in hand. Why is that? Well, as you can see, any point on this shape, let's say this point over here, that is 5, 3, is brought to this point over here, 7.3 and 3, right? This tip right here, that is 4, 4, is brought to 5.9, 4. So what's going on here is that the magnitude along the y is preserved, whereas the magnitude along the x is amplified by 1.48. It happens that one eigenvalue is 1.48, and its corresponding eigenvector is the unit vector pointing towards the x-axis. That is 1, 0. Why is that? Well, any point that is pointing along 1, 0, this vector over here, the x-axis in other words, will remain on the x-axis after this transformation. So as you can see, this line over here will just be extended. It won't be shifted or rotated. Well, when does it rotate? Well, let's say we have this transformation. As you can see, the vector 1, 0 is no longer an eigenvector. Okay, the vector pointing towards the x-axis, well, it's no longer, given this other transformation. Other transformations could be as such, shifting and rotating, rotating clockwise, compressing in one direction, and so on, right? So when thinking about eigenvalues and eigenvectors, it's, let's say, appreciated to keep the linear transformation concept in mind, because eigenvectors are specific directions where the transformation is preserved. That is, the direction is kept unchanged. So let's get into a rigorous definition. So now, to concretely define eigenvalues and eigenvectors, we'll start by a matrix A that is square and will always be square. There's no eigenvectors and eigenvalues defined for non-square matrices. Well, I'm not going to talk about this now, but there's a variation of eigenvalues, eigenvectors of this concept towards non-square matrices, and it's called singular values and singular vectors. But we'll not talk about this in the few coming lectures. We'll postpone this till future lectures. Now, in order to find an eigenvalue lambda and its associated eigenvector v, it must be the case that a v is lambda v, right? If you're able to find me simultaneously a scalar lambda and a vector v that satisfy this equation, then guess what? You found an eigenvalue and its corresponding eigenvector, right? Well, if we rewrite this equation, well, we bring the right-hand side to the left-hand side. This is equivalent to a v minus lambda v set to 0, the vector 0, right? And factoring v, we get a minus, not lambda. Many people do this mistake. It's not lambda v. This is wrong. It should be lambda I, okay? The identity matrix I. Because a minus lambda doesn't make sense. Actually, it's not defined. You've got a matrix A minus a scalar. What does that mean? So it's lambda I, okay? Now, this is another way of rewriting this eigenvalue relation. Since v is a non-zero vector, so we're not looking for the trivial solution to this linear system. We're looking for non-trivial solutions, okay? Because 0 will always be, an eigenvector. Look at it. What is a times 0? It's 0. Well, what is a lambda such that lambda v is 0? It's anything. So there's infinite eigenvalues for the specific eigenvector 0. We don't care about this, and we'll be only addressing non-zero eigenvectors, okay? Now, what does that mean? It also means that the matrix A minus lambda I is singular, okay? So it is non-invertible. A minus lambda I, again, is non-invertible. What does that mean? It also means that the determinant of A minus lambda I is 0. This equation is very important, and actually it has a name. So the determinant of A minus lambda I is actually a polynomial of degree n. And the problem of finding the eigenvalues will boil down to finding roots or zeros of the polynomial determinant A minus lambda I. So why not see this determinant as a function of lambda? That is P of lambda. So P of lambda is actually is defined to be the determinant of A minus lambda I. And it is a polynomial, again, of degree n. That is, we can write it as an lambda to the power n plus an minus 1 lambda to the power n minus 1 down to a2 lambda square plus a1 lambda plus a0. And those ak's should not be confused with entries of matrix A. No, they are functions of the entries of matrix A, that's for sure, but they do not necessarily indicate entries, explicit entries of A. Okay? So keep in mind that I'm going to give you a small remark over here. Since P of lambda is of degree n, so the degree of P of lambda is n, this means that P of lambda, this applies in the real field, has exactly n roots, or n zeros, or n solutions. And any complex roots occur if this is our case, when the coefficients are real, an minus 1 down to a2, a1, a0. When those guys are real, which is our case, then in case you get complex roots, they appear in conjugate pairs. So an example on what I just said is the following polynomial. Imagine you've got a P of lambda that is, I don't know, let's say lambda cubed plus 2 lambda square plus 3 lambda plus, I don't know, let's say 6. Well, this polynomial, you can go ahead and verify that it has a real root, that is lambda 0 is, I don't know, that is lambda 0 equal to minus 2, and two complex roots, lambda 1 and lambda 2, that are root 3i and minus root 3i. As you can see, they appear in conjugate pairs. Well, this doesn't only apply to this application, it applies to any polynomial with real coefficients. Okay? So this is always going to be our case for the next lectures. And the reason why is that A is a real matrix that will lead us to a polynomial P lambda with real coefficients. And hence, in case we get complex roots, well, they appear in conjugate pairs. Now, this polynomial of degree n may have one or more roots of multiplicity 2 or more. That said, you can encounter the following example. An easy, straightforward example is the following. Let's say P of lambda is lambda minus 3 cubed, for example, or square. Let's keep it lambda minus 3 square. So this is example 1, and this is example 2. This could be written as lambda square minus 6 lambda plus 9. Well, what are the roots of P? They are lambda 0, which is the same as lambda 1, which is 3. So we got two roots that are equal. We say that this root 3 is of multiplicity 2. That is, it appears twice. We also say that the root 3 is counted 2 times or twice. Okay? Now, keep in mind one thing. This polynomial P is called the characteristic equation of matrix A. Okay? Now, I know I've said a lot of stuff over here, but it's really worthy to rewrite the eigenvalue relation in different ways, because this relation led us to this, which led us to this, and finally to this very important polynomial. Because really, this is how we're going to find the eigenvalues. This is the classical way of detecting the eigenvalues. So more formally, if A is a real square matrix, then the polynomial p lambda that is defined as determinant of A minus lambda I is called the characteristic polynomial. Actually, this equation over here should be replaced by polynomial. The term equation is when you set the characteristic polynomial to 0. So p lambda equals 0 is called the characteristic equation. Okay? So again, why do we care about p of lambda? Well, if a particular lambda, call it lambda naught, is a root of p of lambda, that is, p of lambda naught is 0, then lambda 0 is an eigenvalue of matrix A. And even more, if vector v0 is a non-zero column vector satisfying a v0 is lambda 0 v0, then v0 is an eigenvector of A. And it is, associated to lambda 0. So let's give an example on eigenvalues, eigenvectors. So an example on this would be, say we've got a matrix, let's say 2, 1, and 1, 2, okay? And you're asked to, and let's say we're given two vectors, v0, that is minus 1, 1, and v1, that is 1, 1. And we're curious to know if any of the two vectors are indeed eigenvectors or not. What we have to do is just to see if is a v a scalar multiple of v. That's what you have to ask yourself. Well, we start with a v0, that is 2, 1, 1, 2 by minus 1 and 1. That gives us minus 1 and 1. So it didn't only give me lambda v0, it returned v0 as is. So what do we say? We say that v0 is an eigenvector with eigenvalue lambda 0 is 1. Now let's check v1. So av1 is following product, that is 3, 3. Now is this a scalar multiple of v1? Well, yes. Why? Because you can write it as 3 times 1, 1. That is 3v1. So we say that v1 is also an eigenvector with eigenvalue lambda 1 is 3, right? Right, so back to the horse example. Let's say my transformation matrix is this guy, right? And we would like to visualize how eigenvalues come in place. Well, the first eigenvector is not going to really be of interest over here. And that's because it's pointing towards minus 1 and 1. So something like this, right? V1, on the other hand, is going to be an eigenvector of interest. Why? Because we've got a point over here pointing in its direction. That is 3, 3. It lies on the line that is in the direction of 1, 1. Right? So that said, this point over here will be transformed to the point on the same line, right? And even more, since the eigenvalue is 3, then guess what? Those points over here will be multiplied by 3. And just forget the decimal notation for now. It's just that I didn't manage to get the point on the exact point. I got it somewhere next to it. Well, it should be 9 by 9. So the point that we transformed is not rotating, is not doing anything other than being amplified on the same direction. So 3, 3 becomes a 9, 9. And that's what eigenvectors, eigenvalues reflect. After transformation, the point preserves direction and is either elongated or compressed. In this case, it's elongated because the eigenvalue 3 is greater than 1. Okay? So in this case, we got a multiplicity of 1 per eigenvalue. So 1 showed in ones and minus 1 and 3 showed in ones. We didn't see an eigenvalue with 2 eigenvectors, even though this is possible. Now, let's say we want a procedure to find eigenvalues and eigenvectors. Here, in this example, I gave you 2 vectors, and I told you to test if those vectors are indeed eigenvectors or not. Well, let's say I'm only given the matrix A without the eigenvectors v0 and v1. Well, there is a procedure for that, and the way of doing so is, given A is n by n, how do we proceed? So 1, we find the characteristic polynomial p of lambda that is defined by the determinant of A minus lambda I. 2, we compute using what you know in calculus, really this is not really sophisticated. So compute n roots of the characteristic equation p of lambda is 0, right? The roots are labeled by lambda 1 down to lambda n. So n roots. Those are the eigenvalues of A. Now 3, for each distinct lambda I, so we find vectors such that a vi is lambda I vi. By, you can do this however you want, but usually what people do is solve A minus lambda I vi is 0. Solve this homogeneous system. Now, in case lambda I is of multiple roots, we'll see this later on, there may be only one associated eigenvector. If not, just compute the distinct eigenvectors. Okay? So this is the procedure. This is how you do it. So let's do an example. Taking the same matrix A, that is 2, 1, 1, 2, and try to figure out, without any given vectors, the eigenvalues and eigenvectors of A. So applying this procedure, first compute the characteristic polynomial p of lambda, that is the determinant of A minus lambda I, that is the determinant of A, that is 2, 1, 1, 2, and lambda I is always an identity with lambda on its diagonal components, right? So doing the math, we get the determinant of 2 minus lambda here, 1 minus 0, that is 1, 1 minus 0, that is 1, and 2 minus lambda again. The determinant, we do this cross thing to get 2 minus lambda times 2 minus lambda, that is 2 minus lambda square, minus 1 times 1, that is 1, right? You could also write this as lambda minus 2 square minus 1. Now here, to go to step 2, you want to find the roots. Well, from what you know in calculus, finding roots of polynomials are easily done when the polynomial is factored. So using really an identity here, that is a square minus b square is a minus b into a plus b. So we get lambda minus 2 minus 1 into lambda minus 2 plus 1, right? That is lambda minus 3 times lambda minus 1. Now, writing down the characteristic equation, p of lambda equals 0, we grab the factored form of p of lambda, that is lambda minus 3 into lambda minus 1, that is 0. This is the equivalent of saying lambda 1 is 3, so the roots are lambda 1 is 3 and lambda 2 is 1. So we successfully got the eigenvalues of A that are 3 and 1. Going down to the last step, that is, for each lambda I, we find a vector vi that satisfies the eigenvalue relation, either by solving this or this. So doing this here, let's grab lambda 1 equal 3 first. So A vi is lambda I vi. So for lambda 1 equal 3, we want to find v1 such that a v1 is 3 v1, right? Now we replace A is 2 1 1 2, v1 is unknown, we're trying to find it. This is 3 v1. Now if you denote by v1 a vector of unknown components, let's say x and y, the problem is to find your x and y, right? So 2 1 1 2 multiplied by a vector of xy is nothing other than 3x and 3y, right? Doing the math, what you get is 2x plus y, the first component, and x plus 2y in the second one. That is equal to, again, 3x and 3y. Well, if we get this vector on the left-hand side, what we get is minus x plus y and x minus y, right? That are both equal to 0. Well, both equations are giving us that x is equal to y, and for that you can pick y is equal to 1 to get x 1, okay? Actually, if you notice, you can pick any y, you can pick it 2 so that its corresponding x is 2. You can pick a y 3, because really here what we care about is the direction. So a direction in the 1 1 sense, it's what we care about. A unit direction. Okay? So one eigenvector, v1, is 1 1. Now doing the same thing for the second eigenvalue, a v2 is lambda 2 v2, where lambda 2 is 1, so a v2 is v2. And again, denoting v2 by xy, performing the multiplication, we get 2x plus y, and x plus 2y is equal to xy, right? Getting this guy over here, we get x plus y, and also x plus y, that is 0 0. So we get x is minus y, right? You can pick y to be 1 so that your x is minus 1. So v2 is 1 minus 1, or even minus 1 1, right? Going back up here, we get the same results. Lambda 1 here is 1. Now I didn't do the numbering correctly, but that doesn't matter. All what matters is an eigenvalue is matched with its suitable eigenvector. So 3 is matched to the eigenvector 1 1, and 1 is matched with its eigenvector minus 1 1. Okay? Now let's see some more interesting examples. Let's say I've got the following 3 by 3 matrix. A, that is 4 8 3, 0 minus 1 0, and 0 minus 2 and 2. Let's compute the characteristic polynomial, that is determinant of a minus lambda I, which is the determinant of 4 minus lambda, 8 3, 0 minus 1 minus lambda, and a 0, 0 minus 2, and 2 minus lambda. Well, since this column is all zeros except the first component, so we'll compute the determinant based on that, and hence we'll get 4 minus lambda times the determinant of this matrix over here, right? That is minus 1 minus lambda into 2 minus lambda minus 0 times minus 2. So this is what we get. And hence, computing the eigenvalues is as simple as finding the roots of this polynomial. We get lambda 1 is 4 from this factor. Lambda 2 is minus 1 from this factor. And lambda 3 is 2 from this factor. So now we found the eigenvalues. So let's find the eigenvectors. So in this example, instead of solving for a vi is lambda I vi, we're going to use the other form. That is the one over here. Okay, a minus lambda I times I, all multiplied by vi is 0. So instead of this, we'll be using this. So what is a minus lambda I times I? Actually, what is a minus lambda I? It's this form over here. So writing it down over here, 4 minus lambda, 8 and 3, 0 minus 1 minus lambda multiplied by 0, 0 minus 2 and 2 minus lambda, all multiplied by a vector vi of components x, y, and z is the vector of zeros, right? Now, we've got 3 vectors of this form that we need to find. v1, that is linked to lambda 1, v2, associated to lambda 2, and likewise v3 associated to lambda 3. So this is the a minus lambda I. So at lambda I equal to 4, so for lambda 1, what do we get? So all you have to do is replace lambda with 4 and then compute. So 4 minus 4 is 0. Then the rest are unchanged. Minus 1 minus 4 is minus 5. And 2 minus 4 is minus 2. So this is a homogeneous system that we can easily solve through Gaussian elimination. So what we need to do is just null this guy out, because this and this are already 0. So all we have to do is write this down here and perform one step of Gaussian elimination. That is, instead of R3, we put in R3 minus 2 over 5 R2, right? What do we get? The first 2 rows are unchanged, whereas the last one becomes 0, 0, and minus 2, right? So we're still solving. Do not forget the important property of Gaussian elimination, that is, any row operation done on the matrix will give us the same solution. So we're still solving for the same system, written differently. And the most efficient way to solve it is by back substitution. So what you get from this system is that, starting from the last equation, we get that z is 0. Also, this equation gives us that y is 0. Whereas the first system gives us that x is free to move in R. Okay? So any value of x would do. We're going to pick x to be 1, and hence the eigenvector is 1, 0, 0, right? So this eigenvector corresponds to the eigenvalue lambda 1 equal to 4. Now the same thing here. We're going to do the same thing for lambda 2, that is minus 1. What we get is the following system. So instead of lambda, we plug in minus 1 over in the a minus lambda I matrix. We get 5, 8, 3, all zeros, and 0, minus 2, and 3. Multiply it with x, y, z to get all zeros. So this system is easily solved. The second equation doesn't give us anything. The last equation gives us that y should be 3 over 2z. And the first equation gives us that 5x plus 8y plus 3z is 0, right? placing equation 1 and equation 2, we get that 5x is minus 15, z, that z, x is minus 3z, right? So this is x in terms of z, and this is y in terms of z. So the eigenvector that we're looking for is actually of the form x, so parametrized in terms of z, so x is minus 3z, y is 3 over 2z, and z is z, right? So for z equal to 1, we get minus 3, 3 over 2, and 1. So this is one possible eigenvector corresponding to lambda 2 is minus 1, okay? Now for the last eigenvalue, that is lambda 3 equal 2, we replace this value in a minus lambda I to get 2, 8, 3, 0, minus 3, 0, and 0, minus 2, 0. The way you can solve is whatever way really. So this equation gives us that y is 0, and this equation gives us the same thing. So we get that y is 0. Plugging it in the first equation, that is 2x plus 8y plus 3z. So this guy goes out, this is 0. You get that x is minus 3 over 2z, okay? And y is 0. So the eigenvector we're looking for, v3, is actually of the form minus 3 over 2z, y is 0, and z is z. For z equal to 1, we get a possible eigenvector that is associated to lambda 2 is equal to 2. One last example is on the matrix A, that is the all ones matrix, so 1 everywhere. Writing down the characteristic equation, that is the determinant of A minus lambda I, which you can write down as lambda squared into lambda minus 3. That means that lambda equals 0 is of multiplicity 2 and lambda equal 3. Well, in this case, if we want to find the eigenvector corresponding to lambda equals 0, what do we get? So for lambda equals 0, we get that A minus lambda I is of the form 1, 1, 1, 1, 1, 1, all ones, so A, in other words, multiplied by V, so this guy is V, is all zeros. So using Gaussian elimination, we can do some row operations to get the following matrix, which means that x is minus y minus z from the first equation, and that's it. That's all the equations you get. The second and third equations are useless. It gives you 0, 0, right? So what does that mean? It means that any solution of this form, so if v1 is of the following form, minus y minus z, y, z, which could be written as two linearly independent vectors that are one in terms of y and the other is in terms of z, right? So there's two v's over here, this one and this one, v1 and v2, for the same eigenvalue lambda. So in this case, we get two eigenvectors for lambda equals 0. And for lambda 2 equal 3, you're going to get only one eigenvector because it's of multiplicity 1. So note that the matrix in this example is symmetric. Whenever a real matrix is symmetric, it has n linearly independent eigenvectors, even if its characteristic equation has roots of multiplicity 2 or more. We will see this in future lectures, but keep this in mind. Okay, so that's about it. We introduced you to eigenvectors, eigenvalues, what a characteristic equation is, a well-known procedure on computing eigenvalues and eigenvectors, how you can interpret eigenvectors and eigenvalues geometrically, and we gave a few examples over here. Thank you for watching. If you found this lecture beneficial, please leave a like on the video, subscribe to the channel. If you have any questions whatsoever, kindly leave a comment down in the comment section below, and I'll make sure I'll get to it as soon as possible. Thank you so much, and I'll see you in future lectures.